Look around you for a moment. Everything you've ever known is sitting on a giant ball that's racing through space at incredible speed. Now here's the strange part. If there's nothing underneath the Earth, why isn't it simply falling into the endless darkness? The answer reveals one of the deepest ideas in physics, and once you understand it, you'll never look at the sky the same way again. Imagine standing outside on a clear night. You look up and see the stars scattered across the darkness. The earth beneath your feet feels solid, stable, and motionless. It feels as though you're standing on something permanent. Yet the moment you begin to think carefully about it, a strange question appears. What is actually holding the earth up? Sounds like a simple question. After all, when something is above the ground, we expect it to be supported by something underneath. A table is held up by its legs, a chair stands on the floor, a building rests on its foundation. Every experience in our daily lives teaches us that things need support. Remove the support, and things fall. So what is supporting the Earth? If you could travel far away and look back at our planet, you would discover something remarkable. There are no giant pillars underneath it. There is no invisible platform. There are no cosmic ropes hanging from the sky. The Earth is simply there, suspended in the vast emptiness of space. And that leads to an even stranger question. If nothing is holding the Earth up, why doesn't it fall? Now, most people imagine falling as moving downward. But the moment you ask downward, you must ask, downward toward what? Down is a direction that makes sense only because you live on Earth. For someone standing on the opposite side of the planet, their down points in exactly the opposite direction from yours. Yet neither of you feels upside down. This is one of the first clues that our intuition, which works beautifully on everyday scales, begins to fail when we think about the universe. The truth is that space does not come with a built-in up or down. There is no universal floor beneath the planets. There is no cosmic basement waiting underneath the solar system. In space, the concepts of up and down lose their meaning. So when we ask why Earth doesn't fall, we're secretly imagining that there is some giant direction called down that everything should move toward. But the universe doesn't work that way. Still, the mystery remains. If Earth is not supported by anything, what keeps it where it is? To answer that, we have to rethink what motion really means. Suppose you're riding in a perfectly smooth train. The curtains are closed. The ride is so smooth that you cannot see the landscape outside. If the train moves at a constant speed, you may feel as though you're standing completely still. You can toss a ball into the air and it comes right back to your hand. Everything behaves normally. The remarkable thing is that motion itself is not something you can always feel. The Earth is doing something very similar. Right now, as you listen to these words, the Earth is spinning at roughly 1,670 kilometers per hour at the equator. At the same time, it is orbiting the Sun at about 107,000 kilometers per hour. The Sun itself is moving through our galaxy at extraordinary speed. The galaxy is moving through space as well. In other words, you are traveling faster than almost anything you've ever experienced, yet you feel completely still. This tells us something profound. Motion is not the enemy of stability. In fact, motion can create stability. Let's imagine throwing a ball. If you throw it gently, gravity pulls it down, and it lands nearby. Throw it harder, and it travels farther before hitting the ground. Throw it faster still, and it goes even farther. Now imagine a mountain so tall that it rises above most of the atmosphere. From the top of this mountain, imagine throwing the ball faster and faster. As the ball moves forward, gravity continuously pulls it downward. But because the Earth is curved, the ground falls away beneath the ball as it travels. At a certain speed, something astonishing happens. The ball falls toward Earth forever, but never reaches the ground. Why? Because every time gravity pulls it downward, the Earth's surface curves away beneath it at exactly the same rate. The ball is falling continuously, yet it never crashes. That is an orbit. An orbit is not the absence of falling. An orbit is falling that never ends. This is the key idea. The Earth is not avoiding gravity. The Earth is not escaping gravity. The Earth is constantly falling. It is falling around the sun. Every second of every day, gravity pulls the Earth toward the sun. If gravity suddenly vanished, the Earth would not stay where it is. It would shoot off in a straight line into space. At the same time, if Earth's forward motion suddenly disappeared, gravity would pull it directly toward the sun. The reason neither of these things happens is because both effects work together. Gravity constantly pulls inward. Motion constantly carries Earth forward. The result is a graceful cosmic dance we call an orbit. The Earth is perpetually falling toward the sun, but it keeps missing. That sounds absurd at first. How can a planet miss something as enormous as the sun? Yet that is exactly what happens. Imagine swinging a stone attached to a string. The stone wants to travel in a straight line, but the string continuously pulls it inward. The combination creates a circular path. Now remove the string and replace it with gravity. Replace the stone with Earth. Replace your hand with the sun. The same basic idea appears on a scale so vast that the human mind struggles to picture it. What makes this especially beautiful is that the Earth doesn't need engines to stay in orbit. It doesn't need fuel. It doesn't need constant corrections. Once an object is moving through space, it naturally keeps moving unless something changes its motion. This principle is so simple that it almost feels disappointing. We often imagine that the universe must rely on complicated mechanisms hidden behind the scenes. We expect giant cosmic machinery. We expect mysterious forces pushing planets along their paths. Instead, nature reveals something far more elegant. Objects keep doing what they are already doing. That simple fact explains an enormous part of the universe. The Earth keeps moving because nothing significant is stopping it. Gravity continuously bends its path. The result is the orbit we observe. But there is another layer to this story that makes it even more astonishing. For centuries, people thought gravity was a force pulling objects across empty space. It seemed natural enough. The Earth pulls on the moon, the sun pulls on the Earth, everything pulls on everything else. Then physicists discovered a deeper picture. Space itself is not merely emptiness. Space has structure. Space can bend. Space can curve. Massive objects distort the geometry around them. A useful analogy is to imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a depression. Smaller objects rolling nearby naturally follow curved paths. The analogy is not perfect, but it helps us visualize something extraordinary. The sun changes the shape of space around it. The Earth moves through that curved space. In a sense, the Earth is following the natural contours of the universe. What appears to be a mysterious attraction is actually the geometry of space itself. Think about how incredible that idea is. The planet beneath your feet is not hanging from anything. It is not balanced on anything. It is not being carried by anything. It is moving through a curved cosmic landscape created by the presence of mass and energy. And somehow, from this elegant arrangement, entire solar systems emerge. The moon circles Earth. Earth circles the sun. The planets trace their paths. Stars orbit galactic centers. Galaxies move within clusters. Everywhere we look, the universe is filled with objects that are not standing still, but moving in beautiful patterns governed by the same principles. And yet, despite all this motion, life continues peacefully on a small blue planet. You wake up in the morning. You drink coffee. You talk with friends. You go to work. You make plans. All while standing on a world hurtling through space at extraordinary speed. The fact that we rarely notice this is a testament to how smoothly nature operates. The laws governing these motions are astonishingly reliable. The same principles that determine the path of a baseball also guide planets and galaxies. The same gravity that causes an apple to fall helps organize entire solar systems. Nature does not create one set of rules for small things and another for large things. The universe is unified. The patterns repeat. The principles echo across scales. That realization may be one of the most beautiful discoveries humanity has ever made. A simple question about why Earth doesn't fall eventually leads us to understand motion, gravity, orbits, space, and the architecture of the cosmos itself. And perhaps the most surprising part is that the original question contains a hidden assumption. We ask why Earth doesn't fall, as though falling is something to be avoided. But the truth is almost the opposite. Earth survives precisely because it is falling. It is falling in the most perfect way imaginable. It falls continuously around the sun, never crashing and never escaping. That endless fall has lasted for billions of years. Every mountain, every ocean, every forest, every living creature has existed during this cosmic journey. The entire history of civilization has unfolded aboard a planet engaged in a perpetual fall through curved space. And tonight, when you step outside and look at the stars, perhaps you will see something different. You will no longer see a stationary world beneath your feet. You will see a planet racing through the darkness. You will see an orbit that is really an endless fall. You will see gravity not as an invisible rope, but as part of the shape of reality itself. Most importantly, you will recognize that some of the deepest truths in science begin with questions that sound almost childish. Why is the sky blue? Why do things fall? Why does the moon stay up? Why doesn't Earth fall through space? These questions seem simple until you follow them honestly. Then they open doors into ideas so profound that they change the way you see existence itself. The universe often hides its greatest secrets behind the simplest questions. And when we finally uncover the answer, we discover something remarkable. Reality is usually far stranger, far more elegant, and far more beautiful than our first guess ever imagined. Now, there is another fascinating part of this story that people rarely think about. If the Earth is constantly falling around the sun, then why don't we feel that fall? After all, when an elevator suddenly drops even a tiny distance, your stomach notices immediately. When an airplane encounters turbulence, you feel it. So why don't we feel the Earth's enormous journey through space? The answer lies in the fact that everything around us is making the same journey together. You, your house, the oceans, the atmosphere, the mountains, and every living thing on Earth are all moving as one system. There is no sudden change in speed that your body needs to react to. The motion is smooth and continuous. Imagine sitting inside a perfectly smooth airplane that never shakes. If the windows were covered, you might have no idea how fast you were traveling. Whether the plane moved at 100 kilometers per hour or 900 kilometers per hour, your coffee would still sit on the tray table, and the people beside you would appear perfectly still. Motion by itself isn't what you feel. You feel changes in motion. This simple distinction explains an astonishing amount about the universe. The Earth doesn't need to stop moving to feel stable. Stability comes from the predictability of its motion. In fact, if the Earth suddenly stopped orbiting the sun, that would be a catastrophe beyond imagination. Every object on the planet would continue moving at its previous speed due to inertia. The atmosphere would surge across the surface. Oceans would rush over continents. The consequences would be unimaginable. Ironically, what feels stable to us is actually the result of tremendous motion. This idea appears again and again in nature. A bicycle remains upright more easily when it's moving than when it's standing still. A spinning top balances because it spins. A satellite remains in orbit because it moves forward. Sometimes motion creates order rather than destroying it. The universe seems to have discovered this principle long before humans ever noticed it. And the deeper we investigate, the stranger things become. Consider the moon. Many people think of the moon as something floating above Earth. But the moon is also falling. Every second, Earth's gravity pulls on it. If the moon was standing still, it would crash into Earth. But it isn't standing still. It moves sideways fast enough that it continuously misses. The moon is therefore engaged in exactly the same kind of endless fall that Earth experiences around the sun. In a sense, the solar system is a collection of objects all falling together. The Earth falls around the sun. The moon falls around Earth. Artificial satellites fall around Earth. Even the International Space Station is not floating because gravity disappears there. Gravity is still very strong at that altitude. The astronauts appear weightless because the station and everything inside it are all falling together. This is one of those ideas that sounds impossible until you realize it explains everything. Weightlessness is not the absence of gravity. It is the experience of falling freely. The astronauts are constantly falling toward Earth. But because they are moving forward so quickly, they keep missing the surface. The result looks like floating. Once you understand this, you begin seeing orbits everywhere. An orbit is not a special place. It is not a magical region where gravity stops working. It is simply a particular kind of motion. The distinction is important because it changes how we think about our place in the universe. People often imagine Earth as a kind of cosmic center, a stable platform surrounded by moving objects. But physics reveals something very different. Nothing is truly standing still. Every object is moving relative to something else. The Earth moves around the sun. The sun moves around the center of the galaxy. The galaxy moves relative to neighboring galaxies. Entire galaxy clusters drift through the expanding universe. The search for an absolute state of rest turns out to be surprisingly difficult. Nature seems less interested in stillness than in relationships between motions. And this raises another curious question. If everything is moving, how do we know where anything actually is? The answer is that position only makes sense relative to something else. You know where your house is relative to your city. Your city exists relative to your country. Your planet exists relative to the sun. The sun exists relative to the galaxy. The deeper we look, the more reality appears to be built from relationships rather than fixed backgrounds. Even the idea of falling begins to change. When a skydiver jumps from an airplane, we say they are falling toward Earth. But from another perspective, Earth is also pulling itself toward the skydiver. Gravity acts between both objects. The Earth moves too, although its enormous mass makes the motion incredibly tiny. Nature does not assign one object as the active participant and the other as the passive one. The interaction belongs to both. This symmetry appears throughout physics. Again and again, ideas that seem obvious from everyday experience turn out to be incomplete when viewed from a broader perspective. The Earth doesn't sit still while things happen around it. The Earth participates. The sun doesn't merely influence the planets. The planets influence the sun as well. Every object contributes to the grand structure of motion, and this leads us to one of the most extraordinary realizations of all. The universe is not held together by supports, it is held together by laws. When people first ask what holds Earth up, they are usually imagining some hidden object, a platform, a pillar, a foundation. But nature provides something more subtle. Instead of physical supports, there are patterns. Instead of pillars, there are relationships. Instead of cosmic scaffolding, there are mathematical rules that govern how matter and energy behave. The Earth remains in its orbit not because something physically props it up, but because the laws of motion and gravity allow such an orbit to exist. This is a profound shift in perspective. The universe doesn't resemble a building resting on foundations. It resembles a dance governed by consistent rules. And once you start seeing reality this way, many old questions transform. The question stops being, what is holding the Earth up? The better question becomes, why does nature permit such stable motion in the first place? That question takes us deeper into the mystery. Why do these laws exist? Why does gravity have the strength it does? Why does space possess the properties that allow planets, stars, and galaxies to form? Science can describe these patterns with extraordinary precision. It can predict eclipses centuries in advance. It can send spacecraft across billions of kilometers and arrive within a tiny target area. It can calculate the motions of planets with astonishing accuracy. Yet beneath every answer lies another question. The deeper we go, the more we discover that understanding does not eliminate wonder. It amplifies it. Every layer of explanation reveals another layer waiting beneath. The Earth orbits the Sun because of gravity and motion. Gravity emerges from the geometry of space-time. Mass and energy shape that geometry. And then we ask why space-time has the properties it does. Curiosity keeps pulling us forward. Each answer becomes a doorway to a larger mystery. Perhaps that is one of the most beautiful aspects of science. The goal is not to remove mystery from the universe. The goal is to replace shallow mystery with deeper mystery. At first, the mystery is, why doesn't Earth fall? Then the mystery becomes, why does falling create orbits? Then it becomes, why does gravity exist? Then it becomes, why is space-time structured the way it is? The horizon keeps moving. And every time we approach it, the universe reveals another layer of elegance. So the next time someone asks, if Earth is floating in space, what is holding it up? The answer is both simple and profound. Nothing is holding it up. The Earth doesn't need a support, a pillar, or a platform beneath it. It is moving through the universe according to laws that have been shaping reality for billions of years. What appears impossible from the perspective of everyday life turns out to be perfectly natural on the scale of the cosmos. And perhaps that's the greatest lesson hidden inside this question. The universe is not obligated to match our intuition. Reality is often stranger than our common sense, yet far more beautiful than our imagination. The moment we stop assuming we already know the answer and start asking honest questions, the world begins to reveal its deepest secrets. A child can ask, why doesn't Earth fall? And that single question can lead us to gravity, motion, space, time, stars, galaxies, and the very structure of reality itself. That is the power of curiosity. Not because curiosity gives us all the answers, but because it teaches us where to look. It reminds us that every great discovery begins with the courage to question what everyone else takes for granted. Tonight, when you look up at the night sky, remember this: you are standing on a world that is not resting on anything. A world racing through space, orbiting a star, carried by laws so elegant that they can guide planets, shape galaxies, and govern the entire cosmos. And yet, out of all that vastness, the most extraordinary thing may be this: the universe has given us the ability to understand it, to ask questions about it, to wonder about it, and to keep exploring it. Because the moment we stop asking, the universe becomes ordinary. But the moment we ask why, it becomes infinite.